Ready to go. Okay, so hopefully you had an enjoyable Thanksgiving. Today we're going to discuss three key aspects of proton NMR spectroscopy. We'll talk about the number of signals in the spectrum and what that tells us. We'll talk about the position of those signals, or the chemical shift, and the information we get from that. And then we'll talk about the integration, or the area under the peaks. So there are four, these are three of the four key features of an NMR spectrum, and we'll list those four key features first before we go into them in depth. And the first one is the number of signals that are present in the spectrum. That tells you how many types of hydrogens are present in the compound. Okay, so the number of signals corresponds to the number of different types of hydrogens in a molecule. The second key feature is the position of the signals. This is also known as the chemical shift. This is a term that we taught you in our last lecture before Thanksgiving. So the position of the signals, or the chemical shift, tells you what kinds of hydrogens are present. Okay, so we have how many types. We can learn what kinds of hydrogens they are. Are they attached to an sp2 carbon or an sp3 carbon? Are they attached to a carbon that has an oxygen or a nitrogen attached to it? This is what we mean by what kinds of hydrogens are present. Then the third feature is the intensity of the peaks, or the integration. This is the area under each peak, and it is obtained by an integration process. That tells us how many of each type of hydrogen is present. Okay. And then last, what we'll find, this will be the topic of our next lecture, is that many of our peaks in an NMR spectrum are not sharp singlets. They are split into doublets or triplets, meaning there's more than one peak per signal. This is known as splitting or multiplicity. And in our next lecture, we'll go into great detail on this topic. But this is very powerful because the splitting of a signal tells us how many neighboring hydrogens there are. And so that allows us to connect different fragments of a structure together to determine the actual structure of a molecule. So let's start out with the first point, the number of signals in a molecule. For molecules such as our example that we have up here on the screen, this is pretty straightforward. Our tert-butyl methyl ether has two different types of hydrogens. The methyl groups of the tert-butyl are all equivalent to each other. And then we have the methoxy, the methyl that's attached to the oxygen. So two different types of hydrogens gives us two signals in our proton NMR. But in some other molecules, more complex molecules, it's harder to tell if hydrogens are equivalent to each other or if they are different. So the book suggests a way to determine if hydrogens are different or if they're equivalent, and it refers to it as the Z-test, replacing each hydrogen with a heteroatom Z, and then seeing if the molecules are either the same or enantiomers, or if they are different from each other, diastereomers. I prefer to use the D-test because if your molecule has a heteroatom, such as a chlorine, then the Z-test doesn't really work so well. But most of our molecules don't have a deuterium present. So if we use the D-test, it's going to be a little bit better, but very similar to what the book mentions. So if you're trying to determine if two hydrogens are equivalent or if they are different, what you do is you replace each hydrogen atom in question. So this is usually two different hydrogen atoms with a deuterium. And then you do this separately so that you generate two different molecules. And then you, if they are the same, or if they are enantiomers, then the hydrogens are equivalent. And they'll give one signal in the proton NMR. But if they are diastereomers, then those hydrogens will be different and they will give different signals. So we have a sample problem from the book that goes through this process, looking at pentane, asking how many different types of hydrogens there are in pentane. And again, I would use deuterium instead of chlorine in case there is a chlorine actually present in your molecule. But what you would find is that over here on the right, you see that we have HA, HB, and HC, three different types of signals in this molecule. So we would have, or three different types of hydrogens would give us three different signals in the proton NMR, okay? So one thing that we learn from this is that all of the hydrogens of a methyl group are equivalent. It doesn't matter which of the three hydrogens in this methyl group we replace with the deuterium, we would get the same compound. And this methyl group is equivalent to that methyl group because it would be one deuteropentane in either case. And then our CH2s, if we replace either of these hydrogens with a deuterium, we would get enantiomers, so that tells us that these hydrogens are equivalent. And because of the symmetry in the molecule, the hydrogens on this carbon and that carbon are equivalent to each other. And then we have the hydrogens in the middle on carbon 3, those are equivalent to each other, but not to any other hydrogens in the molecule. So the net result is three different types of hydrogens in pentane, and therefore we would see three different signals in the proton NMR. So where this gets a little more complicated in terms of determining types of hydrogens, or determining if hydrogens are the same or if they are not equivalent, is when we have double bonds or rings present in our molecules. So just as an example, this particular alkene, HA and HB, are equivalent to each other. There will be one signal in the proton NMR for this molecule. If we replace HA with a deuterium, and then we replace HB with a deuterium separately, those two molecules that we generate those two structures that we generate will be the same molecule. They will be equivalent to each other. Each of these hydrogens is cis to one chlorine and trans to the other chlorine, and so there's no difference in replacing HA versus HB with the deuterium. We get the same compound. However, if we have a chlorine and a bromine on this alkene, now HA is not equivalent to HB. HA is cis to chlorine, trans to bromine. HB is cis to bromine and trans to chlorine. So if we replace each of these hydrogens separately with a deuterium, we would generate two different compounds. They would be diastereomers of each other. And so that tells us that these hydrogens are not equivalent to each other. And in this particular molecule, we would have two signals in the proton NMR. So what this tells us is that we can have hydrogens attached to the same carbon that are not equivalent to each other. That happens in some molecules, usually molecules with alkenes, with rings, or with stereocenters. Here's an alkene that has 3 hydrogens. And if we replace each of these 3 hydrogens separately with a deuterium, we find that they are all distinct. None of them are equivalent to each other. So we would have 3 different signals in the proton NMR of this molecule. Of course, HA is on a different carbon from B and C, and it's a different type of carbon. It bears a chlorine. And then B is cis to the chlorine, and C is trans to the chlorine. So if we replaced B and C with deuterium, we would obtain compounds that would be diastereomers of each other. So we would see 3 signals in the proton NMR of this compound. Okay? So when we have a ring, we'll just draw a molecule with a ring down here. Then things get a little more complicated. Okay, so we have 5 hydrogens in chlorocyclopropane. How many different types of hydrogens do we have? One other point that we need to learn to understand this problem is that hydrogens that are reflected in a plane of symmetry are equivalent to each other. So this molecule, chlorocyclopropane, has a plane of symmetry cutting through the middle of the molecule. The hydrogen that is on the same carbon as the chlorine has no other hydrogens that are equivalent to it. So we'll call that HA. The hydrogens that are cis to HA reflect each other in the plane of symmetry. So those will be equivalent to each other. And then the hydrogens that are trans to HA also reflect each other in the plane of symmetry. And so they're equivalent to each other. So this molecule would also give 3 signals in the proton NMR. And one interesting feature that we learn from this example is that you can have hydrogens on the same carbon that are not equivalent to each other. HB and HC are not equivalent to each other. B is trans to the chlorine. C is cis to the chlorine. And we can have hydrogens on different carbons that are equivalent to each other if we have a plane of symmetry. We have this plane of symmetry. These carbons reflect on each other in that plane of symmetry. So these hydrogens are equivalent, and these hydrogens are equivalent. Okay? And when in doubt, you could use the D test, and you would come to the same conclusion for this molecule that there would be 3 signals in the proton NMR. Okay, so we no longer have iClicker questions for credit, but we are doing iClicker questions for practice. So this particular slide has 2 iClicker questions on it, asking you how many different kinds of hydrogens there are in each of these 2 molecules. And you have the same set of choices for each molecule. So you should pause the video at this point and answer these questions. And then when you've come up with your answers, restart the video and I'll discuss the answers to these questions. Okay, hopefully you paused the video and answered the questions. Let's look at compound number 1. So we have a hydrogen on this carboxylic acid. We have a CH3 group on this ester. And then we have 4 hydrogens on this benzene ring. So, of course, the carboxylic acid hydrogen is its own set. The 3 hydrogens that are part of this ester are another set, and they're all equivalent to each other. So we're up to 2 sets of hydrogens. So the main question becomes, what about these 4 hydrogens? Are any of them equivalent to each other, or are they different? And what you would find if you perform the D-test is that each one of these hydrogens is distinct. Each one has a different relationship to the 2 substituents that are present on the ring. This one is adjacent to the carboxylic acid. This one is adjacent to the ester. This one is 2 carbons away from the acid and 3 carbons away from the ester. This one is 2 carbons away from the ester, 3 carbons away from the acid. So if you perform the D-test, you'll find that each of these 4 hydrogens is separate. There's no symmetry in this molecule, so none of those hydrogens reflect on each other. So we end up with a total of 6 different hydrogens in compound number 1. Compound number 2 is challenging because it's a ring. It's similar to the example we did on the board, the chlorocyclopropane, but a little more challenging because we have 1 more carbon in the ring. So the first thing that we notice is that the hydrogen on the carbon that bears the chlorine is going to be its own type of hydrogen. So we have 1 right here. That's not going to be the same as any other hydrogens. And the second thing we notice about this example is there's a plane of symmetry that cuts diagonally through this molecule. Okay? So the 2 hydrogens that are in the plane of symmetry are not reflecting on any other hydrogens, so they're going to be distinct. They're not going to be equivalent to any other hydrogens in the molecule. So one of these hydrogens is pointing up. It's going to be cis to the chlorine. The other hydrogen is pointing down. It's going to be trans to the chlorine. So those 2 hydrogens are going to be different from each other, and you would find that out if you performed the D-test. So we're up to 1, 2, 3. Now we need to consider the hydrogens on each of these carbons, and those carbons are reflected in the plane of symmetry. So that tells us that the 2 hydrogens that are pointing up, the ones that are cis to the chlorine, will be equivalent to each other. And the 2 hydrogens that are pointing down, that are trans to the chlorine, will be equivalent to each other. And you would find this out if you performed the D-test. You'd end up with molecules that are enantiomers of each other if you performed that D-test. So if we count up all these hydrogens, 1, 2, 3, and then 4 and 5. There's 5 different types of hydrogens in this molecule. So C would be the correct answer for number 2. If you have any questions about determining numbers of types of hydrogens, please ask me in office hours or ask the TAs in their recitations. So there are some vocabulary words associated with the types of hydrogens in a molecule that we need to learn. So we'll go ahead and raise the board. So the first one is homotopic. So homotopic hydrogens are two hydrogens that give the same compound when replaced by deuterium. Okay, so these hydrogens will be identical in the proton NMR and will give a single signal. So here's an example of homotopic hydrogens. This is propane. If we replace HA and HB with deuterium, you see that these molecules are identical. They superimpose on each other. And so that tells us that HA and HB are homotopic hydrogens, and therefore they will give the same signal in the proton NMR. Our next term is enantiotopic. So enantiotopic hydrogens are hydrogens that give enantiomers when replaced by deuterium. And even though enantiotopic hydrogens are not the same as homotopic hydrogens, their impact on proton NMR is the same because enantiotopic hydrogens will also give a single signal and will be equivalent to each other in proton NMR. So here's an example of enantiotopic hydrogens. This is bromoethane, and the CH2 or the methylene hydrogens of bromoethane. If we replace them separately with deuterium, what we find is that these are enantiomers of each other. Okay, you can see the way I've drawn them. They're not superimposable. If we were to rotate one of those structures 180 degrees, you would see that they are mirror images of each other. And so enantiotopic hydrogens, like homotopic hydrogens, will give one signal in the proton NMR. We'll go ahead and write that up here as well. Okay. So there's no difference in the NMR, but we distinguish between these types of hydrogens by using these terms. So it's important to use these terms and to be able to identify enantiotopic or homotopic hydrogens in a proton NMR. So our third term is diastereotopic. So diastereotopic hydrogens, as the name suggests, when you replace them separately with deuterium, you get diastereomers. Okay, so let's take a look at an example. Okay, this is 2-chlorobutane. And the hydrogens that we're looking at are the methylene hydrogens. These are the only ones that would be in question because the hydrogens in a methyl group are all equivalent to each other. And of course, this hydrogen has nothing that it's equivalent to. So the only hydrogens we would be concerned with in terms of being enantiotopic, homotopic, or diastereotopic are these two hydrogens, HA and HB. So if we go ahead and draw the deuterated compounds we get when we apply the D test, here's what we find. Okay, we look at these two compounds. We see that they have two stereocenters, and we see that one of the stereocenters is the same, and the other stereocenter is different. Whenever we have that situation where some but not all of the stereocenters are different, the molecules have to be diastereomers. They are not mirror images of each other, so these have to be diastereomers. Unlike homotopic and enantiotopic hydrogens, diastereotopic hydrogens are different in the NMR. So we would see two signals if we have two hydrogens that are diastereotopic. So HA and HB would each give their own signal in the proton NMR. So then the next question becomes, how many different types of hydrogens are present in 2-chlorobutane? Going from left to right, we have our methyl group, that's 1. The methine CH, that's 2. A and B are each separate, so that's 3 and 4. And then this methyl group is 5. Of course, this methyl group is not the same as that one because there's no plane of symmetry in this molecule. So we would have 5 different types of hydrogens in 2-chlorobutane, and we would expect to see 5 different signals in the proton NMR. Now, it's important to note that you don't always see the number of peaks that you would expect to see. Sometimes you see less because 2 similar peaks might overlap with each other. Diastereotopic hydrogens are different, but they're not hugely different. And so in the real world, A and B might overlap with each other, and you might possibly see 4 signals instead of the 5 that you would be anticipating. So if you're working NMR practice problems or problems on your NMR quiz that you'll get soon, if you end up with less peaks than what you're expecting, don't be alarmed. That's just a sign, or it can be attributed to peaks that are overlapping with each other. Okay? All right, so that finishes our discussion of the number of signals or the number of different types of hydrogens that are present in a molecule. Let's talk about the position of those signals or the chemical shift. And we briefly mentioned this topic on Tuesday before Thanksgiving. So in theory, based on the physics behind NMR spectroscopy, we would expect all protons to undergo spin flipping at the same frequency of radio waves. We would expect all carbon-13s to undergo the spin flipping at the same frequency, but they do not. And that is due to the fact that we have electrons in our molecules that are in motion, and having those electrons in motion creates magnetic fields that can either oppose or reinforce the applied magnetic field. So different types of hydrogens will have a different local magnetic field depending on the degree of shielding that we have in the molecule. So this figure here shows this concept well. If we had a proton with no electrons anywhere near it, such a proton does not exist, by the way, but it would only feel the applied magnetic field. But then if we have electron density in the form of sigma bonds or lone pairs, the electrons in sigma bonds and lone pairs will induce a magnetic field that opposes the applied magnetic field. So we say that induced magnetic field caused by the electrons in motion is shielding the nucleus from the magnetic field from the magnet. This proton is feeling a smaller magnetic field because of that shielding effect. And if you remember the diagram that I drew on the board in class on Tuesday, where our x-axis is magnetic field strength, we learned that the difference in energy between the two nuclear spin states depends on the magnetic field strength. So if a given proton is feeling a higher magnetic field strength due to a smaller amount of shielding, there's going to be a bigger difference in energy between the two nuclear spin states. So it will require higher frequency radio waves to cause the spin flipping to occur. And so we will have a higher chemical shift value. In contrast, if we have a set of hydrogens that are shielded, that have a large amount of electrons, either in sigma bonds or lone pairs nearby, that shielding will cause those protons to feel a smaller applied magnetic field, a net magnetic field, I should say. That causes a smaller difference in energy between the two nuclear spin states, and that will allow spin flipping to occur with lower frequency radiation. And the peak for these hydrogens would be at a lower chemical shift value in the proton NMR spectrum. So there's another figure in the book that shows this very nicely. So here would be a case on the left where we had more electron density near the proton, more shielding, smaller net magnetic field or resultant field leads to a lower value. And remember, upfield corresponds to a lower value for chemical shift. De-shielding is the opposite of shielding. If we have electron withdrawing groups, electronegative heteroatoms nearby, those will decrease the electron density of the protons in that vicinity. So you have a smaller induced magnetic field. The protons are feeling a larger amount of the applied field, and therefore higher frequency radiation is required to cause those hydrogens to undergo spin flipping. And remember, a higher number in chemical shift is downfield. And the way that we tried to remember that is to equate downfield with de-shielding. Okay? So the D words are going together. Downfield is going together with de-shielding. Okay? So let's take a look at some of the consequences of this. Let's go over here to this board. And let's look at the chemical shift. Remember, delta, lowercase delta, is our symbol for chemical shift. Let's look at the chemical shifts of methyl groups that are attached to different types of heteroatoms. Okay, we have fluoromethane, we have dimethyl ether, trimethylamine, we have ethane, just two methyl groups bonded to each other. And then we have tetramethylsilane, or TMS, which is the reference compound for NMR spectroscopy. So chemical shift of the methyl groups in fluoromethane, 4.3 ppm. Oxygen is less electronegative than fluorine, de-shielding the methyl groups less than the fluorine would. So the chemical shift in this case is 3.2 ppm. Nitrogen is less electronegative than oxygen. So again, the de-shielding is less. 2.2 ppm is what we see there. Really negligible de-shielding for ethane. And then because silicon is less electronegative than carbon, the electrons in the carbon-silicon bonds are strongly shielding the methyl groups. And so that's the one that we set as the 0 point or the most shielded hydrogens in the proton NMR. So let's take a look at some real spectra. These are compounds that I made myself in my lab many years ago. One of the first projects I worked on in my lab required this compound, required compounds of this type, an alkyne, where on this sp3 carbon bonded to the alkyne, we needed a leaving group. And we have this triethylsilyl group attached to the carbon. We're not going to worry about that right now, but we're going to focus on this sp3 carbon here. So the electron withdrawing effect of the chlorine, that electronegative chlorine, gives us a chemical shift in this case of about 4.1. Okay, for reasons we'll talk about in a moment, the sp carbon also is more electronegative than the sp3 carbon, and so that also withdraws electrons and de-shields to a degree. So what would happen if I made a similar compound, but it had a bromine instead of a chlorine? So bromine is less electronegative than chlorine, so it is less de-shielding. So we would expect the chemical shift to go down to a lower number. We would also say this is an upfield shift. So we take a look. Sure enough, we see the chemical shift went down by about 0.2 ppm. Okay. And then we also made the compound with an iodine here instead of a bromine. We would expect the chemical shift to drop even further. Less de-shielding with an iodine because it's less electronegative than a bromine. Sure enough, it drops again by about 0.2 ppm to 3.7. So we can see a difference, a measurable difference in the chemical shift. Okay. The de-shielding effects are cumulative. I told you this sp carbon can also de-shield in addition to the iodine. So if you have two or more electronegative heteroatoms, you can have increased de-shielding effects. So let's take a look. Chloromethane, dichloromethane. Chloroform is the name for trichloromethane. And we see chemical shifts for the methyl group of 3.1. The methylene group in dichloromethane is 5.3. Chemical shift of the hydrogen in chloroform is 7.3. And then if we had 4 chlorines, carbon tetrachloride, of course, there's no hydrogens here, so there's no chemical shift. Just checking to see if you're paying attention. All right, so there is a table in the book that we'll take a look at of chemical shift values for certain types of hydrogens. The first thing I'll say about this table is please don't memorize the numbers. It's much more important to understand the trends, to understand why a given type of hydrogen will undergo the spin flipping within a certain range of frequencies than it is to have numbers memorized. When we give you compounds and we ask you to predict their NMR, what we want you to do is get the signals in the proper order and not necessarily at the exact correct number. Okay, so memorizing these numbers is really not valuable. But there are some trends that we see. First thing we'll look at is an OH or an NH hydrogen. You see a very wide range, a range of 4 ppm for these types of hydrogens. These kinds of hydrogens can engage in hydrogen bonding, and that strongly impacts their chemical shift. So we can't really pick them out by virtue of their chemical shift values. We'll have another way of determining where these hydrogens are that we'll talk about. Over here, you see that we have CH3 showing up at a lower chemical shift than CH2 or methylene, and a methine, a CH, is at a higher chemical shift. So what we learn from this example here is that carbon is a bit more electronegative than hydrogen. So as we replace hydrogens with alkyl groups, those carbons are slightly de-shielding the neighboring hydrogens, and that's reflected in the higher chemical shift value. Okay, so carbon slightly more electronegative than hydrogen and has a small de-shielding effect. So the other thing we see is that if we have an allylic or a benzylic hydrogen, this would be a hydrogen on an sp3 carbon that is adjacent to an sp2 carbon. It is slightly de-shielded by that electronegative electron withdrawing sp2 carbon. So let's take a look at an example. So this molecule has two methyl groups. The methyl group that is allylic, that's going to have a chemical shift of about 1.5 ppm. And this methyl group over here that is not allylic has a chemical shift of 0.8 ppm. Okay. So sp2 carbons, slightly more electronegative than sp3. So this carbon-carbon bond is slightly polarized towards that sp2 carbon, and it's de-shielding the methyl group, and that's reflected in the difference in chemical shift that we see. Okay, and then as we would expect, hydrogens that are on carbons bearing a heteroatom, nitrogen, oxygen, or a halogen, those are de-shielded. Those show up in the 2.5 to 4 ppm range. But then something that's unexpected is that hydrogens that are directly attached to sp2 carbons are highly de-shielded. Okay, 4.5 to 6 for an alkene, 6.5 to 8 for a benzene ring. But then a hydrogen on an sp carbon is more shielded than these. It's showing up at a lower chemical shift value. So the chemical shifts of hydrogens that are attached to sp2 or sp carbons are not following this pattern of electronegativity causing de-shielding. The reason for that is that those molecules have pi electrons, and those pi electrons are circulating or moving, and having moving pi electrons creates an a magnetic field, and that magnetic field has a different effect than the magnetic fields caused by sigma electrons or lone pairs. So if you are a physics whiz, if you've studied electricity and magnetism, you've learned the right-hand rule, which is how you can predict the directions of magnetic fields. It's been more than 25 years since I took physics, so I can't do that. But here we have a diagram of benzene. We have these pi electrons circulating, and as those pi electrons circulate, an induced magnetic field is created with these particular field lines that we see. We look at where the hydrogen atoms lie in benzene, and we find that they lie in a region where the induced magnetic field is actually reinforcing the applied magnetic field. Okay, so that has a super de-shielding effect. That adds to the magnetic field that is being felt. And so if we erased our diagram, but that puts us in a region where we have a much larger difference in energy between our two nuclear spin states, and will lead to a downfield signal, quite far downfield, in the 6.5 to 8 ppm range for benzene or substituted benzenes. If we look at ethylene, a sample alkene, we see the same thing. The pi electrons of the alkene circulate. The induced magnetic field in the region where the protons lie is going to reinforce the applied magnetic field. So these hydrogens feel a larger magnetic field than simply the one that's coming from the magnet, and therefore require higher frequency radio waves in order to undergo spin flipping. You see that the chemical shift of alkene hydrogens is less generally than the chemical shift of benzene ring hydrogens. That's due to the fact that there are 6 pi electrons in a benzene ring, and only 2 pi electrons in an alkene. And so having more pi electrons leads to a larger, a stronger magnetic field with the benzene ring than what we see with the alkenes. Okay? So that's reflected in the difference in chemical shift between alkenes and benzene rings. So what's happening with alkynes? We take a look at the alkyne, and we see that because of the linear geometry of the alkyne, the hydrogen atom of an alkyne ends up in a region where that induced magnetic field is now opposing the applied magnetic field. These lines curl around, and you see that the magnetic field is now opposing. So the pi electrons of an alkyne have a shielding effect on this hydrogen atom. And so as a result, you have an upfield chemical shift or a lower chemical shift than you would expect based on the electronegativity of the sp carbon. So this table here summarizes the effect of pi electrons on chemical shifts. Hydrogens on benzene rings are highly deshielded. Hydrogens on alkenes are also deshielded, not as much because there's only 2 pi electrons in an alkene, so you have a weaker magnetic field, weaker induced magnetic field than with a benzene ring. And then the hydrogen of an alkyne, because of the linear geometry instead of trigonal planar geometry, the pi electron induced magnetic field shields that hydrogen, leading to a lower chemical shift value. So now we can look at a figure of the spectrum divided up into these regions where different types of hydrogens will show up due to the spin flipping of the nuclei. And we can explain all of these 5 that we see here. We can explain them all by understanding the electronegativity of the heteroatom-based functional groups or the sp2 carbons. And then in the case of the hydrogens that are attached to sp2 carbons or sp carbons, we have to understand the field lines for the induced magnetic field of the pi electrons. If we look at the hydrogens down here, we see that a hydrogen of an aldehyde is extremely deshielded, usually showing up around 9 ppm. It's deshielded by the pi electrons of that carbonyl group. And it's also deshielded by the electronegative oxygen. So having 2 deshielding effects means that aldehyde hydrogens are going to be significantly further downfield than alkene hydrogens. The carboxylic acid hydrogen is usually even further downfield, between 10 to 12 ppm. The issue here is that this hydrogen is involved in strong hydrogen bonds. You might think, wait a minute, those hydrogen bonds should shield the proton. They do not. They actually deshield the proton because hydrogen bonding lengthens the sigma bond and moves this proton further away from the electrons in the oxygen-hydrogen sigma bond. So the net effect of hydrogen bonding lengthens the sigma bond, results in deshielding, and gives you signals in the 10 to 12 region. So please don't memorize the numbers, but you should be able to look at this diagram and understand why each type of hydrogen shows up in the region that it does. Okay, the last thing we're going to talk about in today's lecture is the area under the peaks, or the integration. The intensity of the peaks is directly proportional to the number of hydrogens represented by those peaks. So in our sample molecule, tert-butyl methyl ether, we have 3 times as many hydrogens in the tert-butyl group as we do in the methoxy group, so we have a 3-to-1 ratio. The integration data can be shown in different ways, depending on what kind of instrument you measured the spectrum on and the software that analyzed that data. Sometimes you just get a curve, an integral curve, and what you have to do in that case is take a ruler and just measure the height of those curves. And that's what's going to be proportional to the area under the curves. This curve is 3 times as high as that one. On more modern instruments, you'll get a number, and those numbers are ratios. You can easily see from these numbers that there's a 3-to-1 ratio. Okay? Now, if you know the molecular formula of your molecule, you can figure out how many integration units there are per hydrogen, and therefore figure out how many hydrogens are represented by each signal. And this example from the book shows us how to do that. So we know that this compound has 10 hydrogens. We add up the number of integration units. If you didn't have the units, you would just measure the height of the curve in centimeters, and that would become your units. But in this case, we end up with 110 integration units. Divide that by 10, and we get 11 units per proton. Now there's some error in measuring these. There's the baselines of an NMR spectrum have noise in them. And so these ratios are never going to come out to exact integer ratios. And that's fine. You just round and it works just fine. So if you know that we have 11 units per proton, and we now divide each of these numbers by 11, you see that this signal is 5 hydrogens because we round. This signal is 2 hydrogens. This signal is 3 hydrogens. Okay, so very simple math will allow us to determine the number of hydrogens represented by each signal. And that concludes today's lecture.